Hello everyone, I'm Charles Chege from the Department of Physical and Mathematical Sciences in the School of Pure and Applied Sciences. I'll be presenting to you the unit Biostatistics and under the area Statistical Inference. So first we look at the definition of statistics, then we look at the link between statistics and biology, why we have to involve statistics in biological studies, and then we look at what are the procedures, what is the rationale behind statistical inference, what are you expected to do to have carried out a statistical inference on a certain study of research. Then using collected data, we apply the statistical inference method to make conclusion about a biological study. Now let's first define statistics as a field of science that deals with collection, analysis, interpretation, and presentation of data. The four areas have to be covered collectively for you to have involved in a statistical study. Collection of data, of course, involves going to the field, maybe involving activities like observation, interviews, collection of samples. Then analysis. This is where now we take statistics, common statistics like variance, mean, median, standard deviation, and other measures of statistics. Now, there are two major categories of statistics. One is inferential statistics, where we make inference or conclusions based on samples. In the next step, we are going to define what are samples and how they are different from population. The other type of statistic is descriptive statistics, which studies the conclusions made based on the total population. And of course, we know that sometimes, as a statistician, you're not able to collect data on every member of a population, and you have to take a smaller set of the population to represent the population as a whole. So inferential statistics will be of more use when it comes to data collection and analysis than descriptive statistics. Functions of statistics. One, statistics simplifies data. You can be given mass data that may not contain information that someone can see by looking, but after applying some statistical techniques, you are able to view some information that was contained in the raw facts that you had collected. Statistic also furnishes a technique of comparison. Like you can be able to say, if I got this value as May 20, compared to another value of 30, what does this value of 20 tell me about the study I was carrying out? The other one is test laws of other sciences like biology. You could be having a law, for instance, that in biology, if I want to increase production of a certain type of species like fish, then I have to add the quantity of food that I'm feeding to the fish. So that's a law in science. And you can be able to carry out statistical analysis by first collecting data based on whatever you are carrying out in the research to verify that specific law, that increasing food substance in a certain species of fish increases the production. Then it interprets conditions like, does increasing the food substance fed to the fish increase or decrease production? Then it plays a major role in policy making. Once you're able to carry out this statistical analysis and come up with findings, it's possible to use those findings as a basis of making a decision in a certain situation. Now, we look at key concepts in statistics. One, a population. This is the total number of items of a given type available at a particular time and place. We specify the time and the place when it comes to population, because changing any of these parameters will lead to a change in the consideration you're making at that given time. Just recently we had the census, and you remember that the census was defined on a particular night that it commenced. And that particular night gives a specific time that the census was to be carried out, because the census is all about collecting data about majorly people and other parameters. So the place is the specific point where you get that individual of the population of interest. So if I'm talking about insects that are found somewhere at a place, then I will collect insects that are particularly in that point that I'm studying, not at any other time, because there could be interactions of the insects after some time. Then we have a sample. A sample is a smaller section of the population that is of interest to the researcher and will be used to represent the population as a whole. You can consider this A, B, C, D, E to be a set representing elements in a certain population. But then it could be difficult for us to get every member of this set. So we have to devise a mechanism of selecting some items from here, such that when I use them to carry out statistical analysis, it will be the same as I carried, or close to, as if I carried out the study in the whole number of letters I've written here. So I might decide, I will pick one, skip the other, pick this, skip this, pick this. So now I end up with a smaller set of elements that I can be able to reach. Then all the statistics that I'm going to carry will be based on A, B, and E, and the result I get. Because you see, I was picking one, skipping the other. So that means that the representation I expect from these three could give me a lot of information about the whole sample, about the whole population. So this is how we develop a smaller subset of the population and then use it, like find the mean and the variance of this, and then use that as if they were representing the whole population. Then under this title, we'll be using a hypothesis. A hypothesis is an assumption or an assertion that a researcher makes at the beginning of the study, and then they carry out the statistical research and analysis so that it can be verified. So before you start a study, you have to come up with a hypothesis, a guess, like the number of people increase in time. So if the number of people increase in time for sure, then you go out there and carry out the study of studying how people increase with time. Then you will end up either agreeing with the hypothesis or disagreeing with the hypothesis. So we will have two types of hypothesis. One normally labeled H naught. This one will be called the null hypothesis. And then we will be having an alternative hypothesis labeled H1, which is normally called the alternative hypothesis. Now, eventually, the conclusion you make as a researcher is to, 1, accept H naught, or 2, reject H naught. In which case, if I reject H naught, then I accept H1. At times, we have to consider the possibility of making an error. Like, when I was carrying out a study, maybe there are some parameters I didn't record clearly, and therefore, I ended up rejecting H naught when it was actually true. So if you reject H naught and it is true, we say that you have made type 1 error. So type 1 error is the error of rejecting H naught when it was actually true. Then you might accept H naught when H1 is true. That means you have made type 2 error. So the error of rejecting H naught when it's true is called type 1 error. The error of accepting H naught when it is false is called type 2 error. The other concept is a probability distribution. Now, in this case specifically, we are going to look at the possibility of getting probabilities given a certain function. A function in this case is an expression Although a probability distribution can take form of a table or a graph that gives you corresponding probabilities of a given situation. Now, a probability distribution, if it's a function, we can give an example of a function of what is called exponential distribution. We label probability distributions with f of x. So when someone says f of x is equals to, say, 1 over 2 exponential negative x over 2, then we call this an exponential distribution with parameter lambda is equals to 2. So this type of an expression normally gives you probabilities for values that you obtain, and they are in the form we call continuous case. So if x is written this way, then it means that values of x will range from 0 to infinity in a continuous case, such that the values of x we are talking about here are in an uncountable set of observations. So if for any value of x in this interval I put here, I'm going to get a probability of getting that value of x from this distribution. So consider x is equals to 2. Then because this is a continuous case of a distribution, then we will look at the integral from 0 to 2 of 1 over 2 exponential negative x over 2 with respect to x. So the derivative of this over this interval will give you a corresponding probability. And this is just an example of a distribution. There are several distributions in theory that can be applied in statistical inference, but we will specify and look at one major distribution that is of help when it comes to statistical inference. Now, another concept is that a test statistic. This is an expression that you calculate from the data that you've collected that will help you in making a conclusion to whether accept or reject the null hypothesis. So this conclusion is based on calculating that test statistic and comparing it to what we call a critical value. Now, the importance of the probability distribution is that it gives us corresponding critical values to compare with the test statistic that you calculated. So that if the value of the test statistic you calculated is greater than or equal to the value of the critical, the value of the probability or the critical value from the distribution, then you make a conclusion to reject the null hypothesis. Otherwise, you accept the null hypothesis, although we'll come to that in details. Now, another thing we have to look at is data. Now, we will be analyzing data as statisticians, because once you go to the field, then you have to collect data. Now, this data is just defined as raw facts. And statistics involves now converting these raw facts into what we call information. If you're just given values 2, 3, 4, 6, and say 4 again, and then you're told nothing about these values, then these are just values, they are raw facts. But if you are told that these values represent shoe sizes for a group of 5, then this converts this data into raw facts that have not been processed. You know, if you collected this data and now we want to engage statistics in it, then it will involve calculating some parameters and then interpreting what they mean to us. Then data can be either qualitative or quantitative. In qualitative data, values are ordered in a certain manner that gives meaning. Like, for instance, you can be having 1 to represent poor, maybe, or you can be having 2 fair, and so on, such that there is some order in which these numbers give information. When it comes to quantitative data, it's data that is just listed. This is quantitative data. This is qualitative data, such that when we are analyzing, then we get 2, then it would automatically tell us that on average, a certain person performed fairly. If we get 1, then we can assume that a certain experiment performed poorly. Now, qualitative data can be either discrete or continuous. When data is discrete, like for instance, let's label our data X. If X is continuous, then it takes values in a discrete or in a continuous or finite set. For instance, age. You can be told that the ages of 3 people are 17, 32, and 45. These values are countable. They occur in a finite set. But if X is continuous, on the other hand, then you can be given that X is in the range 0, 1, maybe even inclusive of 0 and 1. So remember, there are uncountable values of X in this interval. We can't be able to count the values in this interval if we say X is in 0, 1, because this interval contains 0.1, 0.001, 0.2, 0.3, 0.9, 0.009. So we can't count the number of values that X can take. But in this case, it's possible to count. So we say such data is continuous because the values of X are contained in an uncountable or infinite set of observations. Now, we look at measurement scales. Of course, when you go to collecting data, you'll have to use a scale. How are you collecting data? Are they values? Are they in an interval? Are they ordered? And so on. So, we look at 4 major types of measurement scales in theory. 1, nominal scale. This is where you just have values. Nominal means numbers, like weight of people. Someone weighs or has a mass of 50 kgs. Another one has 60. Ages. We have someone whose age is 20, 34, 50. Another 17, 45. That is a nominal scale if your data is being recorded in that manner. At times, you have people rating something. Like you tell people to rate a certain president as either being good, bad, fair, maybe very good, and excellent. So these 5 measurements, you're asking people, how would you rate a certain president? Maybe bad is given 1, fair 2, 3 good, very good is 4, and excellent is 5. Now, someone picks any of these letters and it tells you to what level they consider that president to be performing. So that's called ordinal, maybe from the word order. You are ordering these numbers such that you will receive, when you go to analyzing, if you had given a questionnaire, then you'll be analyzing these numbers, but not this. Such that if you get 4, then it means that people think that president is performing very good. The 4th type of scale is called interval scale. This scale is possible for measurements such as rainfall. For instance, consider rainfall of a place being given to be in the interval 550 ml to 1280 milliliters. So it means that any value in this interval qualifies as the rainfall for that place, because at a given point, someone has measured the least amount of rainfall received in that region and the highest possible rainfall amount recorded in that region, and they have given you an interval. So you expect that in a certain given time, you record rainfall in such place, you're going to get something to that. So we have 2 values, a lower and an upper, and values are considered to come from that interval. The last one is the ratio scale. The ratio scale is the strongest measurement scale that we have, because it captures both the scale and the magnitude. The magnitude between the observation. So it has a scale of observation and the magnitude. For instance, a salary of 50,000 is twice as large as a salary of 25. But you go back to interval scale. It is not possible to give the rainfall of a place compared of a point compared to another in such a manner. So the ratio scale is the one that is commonly used in statistics because it has some comparative capabilities. Now we look at sampling design because we had concluded that most times it is not possible to collect information from the total number of elements that are contained in a certain area of study in your research. So eventually, a researcher has to narrow down and come up with a smaller section of the population, avoiding as much bias as possible to come up with the representation of the whole population. So a sample design is a definite statistical plan concerned with all the major steps taken in the section of a sample and estimation procedures. So sampling methods that you can apply in coming up with a sample. One, we will categorize them into two. One, we have random or probabilistic sampling. Now this includes the following methods. One, simple random sampling, where every item in the population has an equal chance of being used. This one helps in reducing bias. So what are we saying? Now, consider the following values. If I want to get a random sample from this, I will not divide this into any value. I might just decide to pick every second value in this data set. So I'll pick this, 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 in that order. So there is no value that has a higher chance of being collected from this sample. Someone else might decide, I'll take a smaller sample, but take every third value in this set. So they are going to pick the third value from each of these sets. You notice that at least we are getting a value from each of every 4 rows we are having. Someone might decide to pick the middle values of every of the 4 rows. So there is no value in this case that has been given priority over the other in collection. The other type of random sampling is stratified. So the same case I was having here, if I had 1, 4, 6, again 7, 8, 9, 10, 11, 12, then I have 13, 14, 15, then I might decide to divide into 4. And then at least pick each of these from this set. Or I can decide I'll take the mean of each. So first, divide the data into the sampling, divide into groups in such a way that the groups are similar as possible, then pick a value from each of the classes. Note that someone else might decide to divide this way and maybe have 3 groups and then take 2 from each group, such that in that way we will have 3 clusters or 3 groups to select from. The other one is systematic sampling. In this, samples are drawn using some predetermined objects. Like I might say, I'll pick all the odd numbers here. So I'll take 1, 7, 9, 11, 13, and 15. So you use some predetermined for a given reason. You pick odd numbers. For a given reason, someone decides I'll take even numbers. So there is some predetermined thing that you're using to determine whether to take even or odd numbers. So if we want to draw a sample of size n, then we divide the population into equal parts. n equal parts, and then pick a part from each. So the discretion is at the researcher's opinion on what to use to, or what predetermined characteristics in the data they've used to set. Then we have multi-stage sampling. So in this method, the population is first divided into simple sampling units using simple random sampling. So first divide into classes using without bias. Then the units are selected, are then subdivided into a second stage. So in this case, first divide the first time, then from there, divide again. For instance, again, from the same sample, if I have 7, 8, 9, then 10, 11, 12, then 13, 14, 15, first divide. Then from here, I have odd and even. Here I have 2 odd and 1 even. Then in this case I have 1 odd, that is 11, and 2 even. Then in this case I have 2 odd and 1 even. So first I grouped them. Then again I grouped them into what type of numbers they are. Then you can decide that you will pick at least 1 and 1 of the one that is a pair, or the greater one or the smaller one, depending on what the researcher is looking at. You then choose from these second groups that you have selected. The other category is non-random sampling. So this does not involve any probabilistic measures, and it has 4 methods under it. One, there is judgmental sampling, where the choice of the sample depends exclusively on the judgment of the investigator. So the investigator decides where to pick. The reason it depends with what study they are carrying. So if I'm carrying out a study on students, I might decide that I'll take students who are in their 4th year of study only. Maybe it's because of my research. Maybe my research depends on whichever level of study someone is. So exclusively, I pick students that are in the 4th year of study from my own judgment as the researcher. Then we have cluster sampling, in which group of elementary units are formed generally based on location. So then, in this class, we have clusters. You might form clusters based on the department of the student, such that you say, I'll pick 5 departments, pick Department A, Department B, Department C, Department D, and then now decide from that department. You might decide to pick students that are taking a certain unit from that department, but first you selected according to clusters. In this case, our clusters are the departments. Then we have quarter sampling. This occurs when the investigator are to interview the population up to a certain quarter. So you're told we want a 400 quarter of females that are in Mount Kenya University. So you're given a quarter of 400. So you're going to pick those people until that quarter is satisfied. So pick 250 working wives, take 150 work wives, then 150 working wives, then 100 unmarried wives. So that at least, if you add them, you're going to get a total of 400 according to the quarter. Now, in statistical inference, certain measures will be very important, and that is, 1, the mean. We will be using the mean, and in this case, the mean is usually the average of a set of numbers. Now, the average of a set of numbers normally is under the category of statistics called measures of central tendency. These measures include mode, mean, and median. So these measures are normally called measures of central tendency because they tend to classify data according to where it is centrally placed. Look at the example of 1, 2, 3, 4, and 5. Now, assuming that these are maybe heights of plants in a garden, assuming you have 6 types of plants, then we are saying that these measures will just ask the question, where do we find a central point in this set of ordered data? And then they will try to calculate that point and then use that to as if you're referring to the whole population. So in this case, a plant that has a height of 1 centimeter will be reported as a plant that is having a height of 3 centimeters. A plant that has a 5 centimeters height will be reported as a plant that has maybe 3 centimeters. So in that case, we call measures of central tendency crude measures, because we would expect a better measure that maybe tells us, if we have a central point, then a plant that weighs a height of 1 centimeters, how far is it from that central point? That would be a better measure, because at least it gives us an insight into the magnitude of the difference between the expected and the observed. Now, the mean, formal definition in statistics, consider a set of random variables, x1, x2, all the way to xn. Now, x1 in this case would be the value 1, x2 would be the value 2, x3 would be 3, x4 would be 3, x5 would be 4, and x6 would be 5. In that case, in this definition, n is 6. So just saying random variables, we just talk of numbers that have been generated without a predetermined argument. So let x1, x2, all the way to xn be a set of n random variables. In my case here, n is 6. The mean is given as these are the abbreviations for the mean. Mean is normally abbreviated by x bar. Sometimes we talk of mu of x, where mu is a Greek alphabet. So this is obtained as the summation of values of x divided by the number of observations n. We notice that in this case I had n observations being 6. So I will take the summation of the values of x, then divide by number of observation. So looking for my mean in this case, then I would have 1 plus 2 plus 3 plus 3 plus 4 plus 5 divide by 6. In this case, the mean is 3. That's how we get the average of a set of numbers. Of course, we may consider a case where you've been asked to get the mean, or the median and the mode. For ungrouped data like the one we are having there, 5, then the mode represents the value that occurs most. So if you look at this set, then we only have one repeated digit, and that is 3. So 3 is the mode. We can also consider the median as another statistical measure. Now, the median is normally the value that occurs in the middle when the data is ordered. That means it is arranged in either ascending or descending order. So if I have 1, 2, 3, 3, 4, 5, then the value that occurs in the middle, we can single out and see what happens. We have that goes with that, this goes with this. And then you notice that in the middle here, the values are 2, and we don't have a value that is occurring in the middle there. So we can get the average, because the value that is occurring in the middle here is the median. So we can get the median by adding 3 and 3 and then dividing by the 2. That is getting the average of the 2 values occurring in the middle, which again gives us 6/2, which is 3. So we notice that both the mean, the median, and the mode give us the same value, which is the measure of central tendency in this case. So if I was to repeat, if I was to report these data, then it means that I would be reporting a plant that has a height of 1 to be having a height of 3, and a plant that has a height of 5 to be having a height of 3. And as I said, that means that these are crude measures because they had nothing they tell us about the association or the link between the value that is occurring in the middle and the value that is less or greater than that value. Now, let's look at another statistic, that is the variance. Now, the variance is in a category of statistics called measures of dispersion. Now, unlike the measures of central tendency, measures of dispersion, they are able to tell us the spread of values from a certain central point. Actually, the definition of variance is it is a measure of spread from the central mean. So the variance asks the question, how far are certain observations from the value that we obtained from the mean? In that case, variance of x, also normally labeled by the Greek symbol sigma squared of x, is normally obtained as 1, that is when we have ungrouped data, 1 over n, then you sum each of the observations minus the mean squared. So you can see that this is every observation. So if x is 1, then if x is 1, then I'm talking about the height of a plant being 1. In the case where we had the data set 1, 2, 3, 4, and 5, then the first value x1 is 1. So I'm taking the value, subtracting the mean, because we got the mean of this set, the set of data is 3, then squaring the result. And we'll do that for each of these values and then sum them. That gives us the variance. So let's look at the same example and attempt to get the variance of them. So our x values are 1. Let's create a table for this. Then we can have our x minus x bar. And then we can square x minus x bar squared. Now we have 1, we have 2, we have 3, we have 4, and we have 5. Now, we got x bar for the same set of data as 3. So in this case, then we'll be taking each value in x, subtracting 3. So 1 minus 3 is negative 2. Then 2 minus 3 is negative 1. This would make 0, and I missed one value, which is 3. So there is 3, which makes 0 because of 3 minus 3. Then there is 3 again, which makes 0. Then there is 4 minus 3, which is 1, and then 5 minus 3, which is 2. Then from this formula, then we need to square these values. So negative 2 squared, note that is negative 2 times negative 2, which is makes positive 4. Then we have negative 1 squared, which is 1, then 0, 0, and then these would be 1, and these would be 4. So the summation of these values is 10. Therefore, sigma squared of x, the variance, will be 1 over 6, then 10, of which this makes 10 over 6, 5 over 10 over 6, or 5 over 3. So this is the variance. It is measuring the spread of values, considering that they have a point, a central mean at 3. We need also to note that another measure that is close to the variance is the standard deviation, where the standard deviation of x, normally abbreviated by SD, is given as the square root of the variance of x. In this case, then we are looking at the square root of sigma squared x, which is actually sigma of x. So this is the symbol for the standard deviation of x. And if I were to use the same example here, then for me to get the standard deviation of x, then I would square root 5 over 3 to get the standard deviation. Now, in statistical inference, as I had introduced the distribution, the commonly used distribution, and in fact other distributions that are normally used in statistical inference, that is the student's T distribution, the student's F distribution, and the chi distribution, are all derived from the normal distribution. Now, the normal distribution is defined on two parameters. In fact, if a random variable x is believed to be following a normal distribution, then we write it has a normal distribution. Then we define its mean using the symbol mu and the variance using the symbol sigma squared. So if a distribution has a known mean and a known sigma squared, then we say that that distribution follows a normal distribution. Now, the functional representation of the normal distribution is such that f of x is equals to 1 over square root of 2 pi sigma squared, then the exponent of negative 1 over 2 sigma squared x minus mu squared. Now, it is 0 elsewhere, and values of x are in the interval of the real line, negative infinity. So, in this case, for a normal distribution, the value of x can be any value from negative infinity to infinity. Note that we are saying we can be able to get any corresponding probability from a normal distribution given the value of x that we want to get. But then that involves complex integration techniques that have to be applied to get that. And due to that problem, there is a standardization of this, so that evaluation of probabilities corresponding to values of x can be very easy when it comes to the normal distribution. That translates to what we call the standard normal. Distribution. A standard normal distribution is a standardization of the normal distribution using the variate z is equals to x minus mu divided by sigma. Note that this is the value of x with which we want to get its probability. This is the distribution of, this is the mean of the original distribution, and this is the standard deviation of the original distribution. Now, what happens? A standard normal distribution, if z follows a standard normal distribution, then we say that it follows a normal with n, with mu is equals to 0 and variance is equals to 1. So such a distribution has the expression f of x as 1 over root 2 pi, then exponential x squared negative, and it's 0 elsewhere. Of course, with values of x in the interval negative infinity to infinity. Now, these values have been tabulated in what is called the Z table. So, once I'm able to evaluate the values of Z using the values of x I've been given, I can be able to read the corresponding value of Z, probability of Z, from the standard normal table, and hence I'm saved from the hassle of having to integrate the exponential function. The standard normal distribution derivation expression is as follows. Then we can look at an example of how the standard normal table can be used to find the probability of certain values of x given the normal distribution. Now, a random variable x is believed to follow a normal distribution with mu is equals to 20 and sigma squared is equals to 10. Note that in this case, the mean is 20 and the variance is 10. Now, we want to check what is the probability that x is 15. Usually, we would look for probability of x is equals to 15 by integrating from negative infinity to 15 of the f of x, in which the f of x is the original distribution defined for the normal. That is 1 over square root of 2 pi sigma squared exponential negative 1 over 2 sigma squared x minus mu squared. But now, we are saying that this could be tedious, and alternatively, we can first calculate the value of z. Now, the value of z has been defined as x minus mu divided by sigma. Now, our mu is the mean, which has been given as 20. Then, we've been given sigma squared as 10. So that the sigma will be square root of 10. Now, z, therefore, if we want probability that x is 15, then the value of z will be given by 15 minus 20 divided by square root of 10, which gives us 1.58, but with a negative value. Then, the z table can be given either with values of z being positive or values of z being negative. So, in a situation where you've been given the z table being positive, like in this case, you can see that the first column there represents the values of z, and after that, within the matrix, we have probabilities corresponding to the values of z. Now, you observe that the values given in that illustrative table there have z being positive. So, there is no way you can be able to read this from the z. So, what you do, you have to make conversions. That probability there is normally abbreviated by phi inverse. So, we want phi inverse of a negative value of z. This is equivalent to getting 1 minus the probability when z is positive. So, in this case, we observe that the value of z when it's positive in the table will be 0. So, we have 1 minus 0.9429. So, the correct probability that the value of x will be 15 is 0.50571. So, that's how you obtain corresponding probabilities of x using the standard normal distribution, and maybe the other part is left for attempting. Now, we now look at the procedure involved when someone is carrying out a test of hypothesis. 1, you state the hypothesis. Stating the hypothesis includes 1, you state whether the hypothesis in question, you state 1, the null hypothesis, that is what we labeled H0. You also state the alternative hypothesis, that is H1, and also it is important to state what these hypotheses mean. When you say that H0, I'm looking at H0 such that the mean is a certain value, then what does it mean? Does it mean that you are checking that the mean is a different value from the one that you have? You have to state what it means to the researcher. Number 2, you state the distribution based on the null hypothesis. Now, the distribution of the null hypothesis will clearly be defined by the type of statistical conclusion you aimed at. Are you looking at equivalence of mean, difference in mean, and so on? Now, then you calculate the test statistic. We said this is an expression that is used to make a conclusion to either accept or reject the null hypothesis. Now, the test statistics in this case, if you're using a normal distribution, the z-score or the z-variate will be the test statistics. Then you find the critical value based on the level of significance. The level of significance is the level of assurance that you give when you make a conclusion. We have level of significance can be 95, which is the most commonly used. It can be 99% or it can be 90%. Most cases you will not have a level of significance of 100 due to errors. Now then you make a decision to accept or reject the null hypothesis. That one had been commented earlier, that making a conclusion on a statistical hypothesis is either accepting or rejecting the null. Then we conclude that we reject H0 if the value from the test statistic is greater than or equal to the critical value. We can illustrate that with an example. Consider a painkiller manufacturer who believes that the waiting time until a patient is relieved of pain follows a normal distribution with mean 10 and variance 25. Now, a doctor is claiming that patients they have attended to have a waiting time of 7 minutes. That is, the doctor has been observing when they administer the drug, what time patients take until they ask them, do you still feel pain? They say, no, it has been 7 minutes. So the question is, can this claim be true using this assumption by the drug manufacturer? Now, this means that we have to carry out a statistical inference test or a test of hypothesis so that we can make a conclusion whether the doctor's claim is true or not. Now, step number 1, we state the hypothesis. Now, we are stating the hypothesis considering what situation we are having at hand. We have a mean of 10 as the waiting time. That is, after taking several samples, you notice that if you get the mean of that, it's 10. Someone is claiming, no, the mean is 7. So our hypothesis is based on the claim. So that makes our H0. So our H0 will be such that the mean we calculated is no longer 10, but it's now 7. So this means that the doctor's claim can be true. Then the alternative hypothesis is such that the mean is not 7. So this means that the doctor's claim is false. So let's see, eventually, will we disqualify the doctor's claim, or will we side with him? That is possibly the patient's the doctor has administered the drugs to, has been true. Now, next step, we need to calculate the test statistics we will use to make our conclusion. So the test statistic we will use the z-score, where z is x minus mu divided by sigma. So in this case, our mean has been given as 10 and sigma squared, the variance 25, such that our sigma is the square root of variance, which is square root of 25, which is 5. So putting back into our equation, we have z is equals to 7, the value in the null hypothesis, minus the mean, divided by 5. We notice that this is negative 3 over 5, which is actually negative 0.6. So this is the test statistics we'll be using to make a conclusion. But then we are to compare it to the critical value from the standard normal distribution. You notice that we've been given to test at an alpha of 5%. So this means that the level of significance is 1 minus alpha, which is 95%. Now, we notice another property of the normal distribution is that it is normally symmetric. So if I have the mean being in the middle here, then these will represent negative, the corresponding probabilities of negative values. And this will represent the corresponding values for positive case. Now, if I pick equal distances from the mean, then the value I get here should be exactly equal to the value I get on the other side. And that's why this is true. So I'm going to read from the table the value corresponding to a 95% level of confidence, but then because of symmetry, we have to divide by 2. So we are talking about 5% divided by 2, which is 2.5%, which is actually 0.025. And it means that is the same as reading the value on 1 minus 0.025, which is actually 0.975. So in the standard normal table, the value that corresponds to this is the critical value. So we go back to the illustrative table, and we notice that our Z value has been negative 0.6. So we have to convert, because the table is positive, then we are looking for phi of negative Z, which is the same as, rather phi inverse, which is the same as getting phi 1 minus phi inverse of Z, Z. So this will mean that we get Z, we get 1 minus phi inverse of 0.6. So this is the same as 1 minus, if you look at 0.6, 0.6 here, then we have 0.7691. So these would be 9032, 0.2309. Now this value is supposed to be compared to the alpha of 5%. Or alternatively, we look at 0.975 in the table here, and then get the value of Z that corresponds to it. This normally gives a value of 1.96. So Z tabulated is 1.96. Then Z calculated as the test statistics, we got 0.6 negative, but normally we look at the absolute value. So we use these two values to compare and make a decision to either accept or reject the null hypothesis. Now, we reject the null hypothesis. We reject H0 if the Z calculated absolute value is greater than or equal to the Z tabulated at the respective level of significance. In this case, Z calculated has been negative 0.6. That is, its absolute is 0.6. Then, and we notice that this is less than, actually it's strictly less than 1.96. So automatically, we end up failing to reject H0. So the conclusion is we do not have enough evidence to reject H naught. And therefore, what is the conclusion? The doctors claim could be true. So we have ended up making a conclusion that whatever the doctor is saying cannot be assumed. But then let's look at the meaning of what we had been given in this illustration. Now we had been given a mean mu of 10 and a variance of 25. Now mostly we may want to use sigma, the standard deviation, in assessing what it meant to us to have such a distribution. This meant that if the mean mu is 10, then with a standard deviation of 5, it is acceptable to have a spread of up to 15 on the upper side and a spread of up to 5 on the lower side. Now, the implication here is, even if a patient records a pain reliever after 7 minutes, which is within the interval 7 here, then that patient is on range, and therefore we cannot say that the pain cannot be relieved with 7 minutes, because if you look at a confidence interval, the range of values that are acceptable in this case, they range from 5 to 15. And therefore, 7 being in this interval, it is okay, and we can see that it conforms to the statistical inference test we have carried out that the doctor's claim is true. In fact, 7 is way above the lower limit of this interval. Now, let's advance a little and look at what if you have 2 samples you are considering, and then you're asking yourself, is there really a difference between these 2 samples? Like, consider a situation whereby now we have decided that the manufacturer who was making painkillers has decided to improve the quality of the medicine, and they have decided to add a certain component of the medicine to check if it improves the time for which a patient has to wait until they feel pain reliever. Now, that means that we can have 2 sets of patients where set A maybe takes the older medicine, and then type B takes the new medicine, such that we will record the time the 2 groups of patients wait until they don't feel pain when they take the medicine. So from that set of data given there, that is 9, 10, 13, 8, 14, 15, 9, 8, 10, and 9, then we can carry out a test for equality of means, such that if the means will end up being equal, then we will make a conclusion that improving or adding an ingredient to the medicine, that ingredient that was added by the manufacturer, had no effect on improving the quality of the medicine. But if the means are different, then it means that the ingredient brought about some effect in the medicine, and maybe it should be considered, of which in this case now we could go deeper and test, did it have an increased or decreased effect on the quality of the medicine. So that would mean we carry a test to ascertain whether the one mean is greater than the other or less than the other. So the other set of data is 7, 14, then 12, 10, 7, then we have 8, 8, 12, 11, and 6. Now, the type of tests used in this case is called a t-test. Now, this means that we are going to apply a new form of distribution known as the t-students t-distribution, which actually is an improvement of the normal distribution. So a t-test in this case is defined as x bar A minus x bar B, and this is minus mu A minus mu B divided by square root of the sigma squared of A all over NA plus sigma squared of B all over NB. So this is the test statistic we are going to use to carry out such a test of hypothesis. This is the mean of this set. This is the mean of this set. This is the mean that we want to check whether they are equal, the mean of A and the mean of the mu of B. Then this is the variance of A divided by the number of observations in A. This is the variance of B divided by the number of observations in B. Now, this is the test statistic. We are going to compare this to the critical value from the student's t distribution with degrees of freedom, because the student's t distribution, unlike the normal distribution, changes with regard to the degrees of freedom. In statistics, the degrees of freedom represents the number of observations in a problem. You subtract the number of parameters that you have estimated. So the degrees of freedom in this case will be given by number of observations in A minus plus number of observations in B, then you minus 1 for this case specifically. This is how we get the degrees of freedom. So we can now calculate and carry out this test. You know, we want to improve the quality of medicine. Our pharmaceutical company has increased the concentration of an ingredient and given the two types of medicine to two groups of patients. Group A is taking the old medicine and Group B is taking the improved medicine. The time until the effect of both medicine is felt are shown below. We have that set. So can we conclude that increasing the concentration of the ingredients had improved the quality of medicine? And we are told to use an alpha of 5%. So again, step 1, we need to state the hypothesis by first stating the null hypothesis. And in this one, we are checking whether the two means are equal. So we want to check whether mu A minus mu B is equals to 0. This means the ingredient had no effect on the quality of medicine. Then we define H1. The alternative hypothesis to compare to the H0 is mu A minus mu B is not equal to 0, such that here we will say that the ingredient had an effect on the medicine, on the quality of medicine. So that after we make a conclusion, then this is what we were looking for, to either disqualify or side with improving the quality of the medicine. Then we find the t-test, or rather the test statistic. The test statistic, as we have defined, is x bar A, which is the mean of A, minus x bar B, then minus the definition in H0, course, divide by an expression for the standard deviation of the two samples, which is over NA plus all over NB. So replacing back the mean as calculated over there, the mean of A is 10.5, the mean of B is 9.5. So we will have T test being equals to 10.5 minus 9.5. Then in this case we are minusing 0 because this test is based on H naught, and we have seen under H naught we are testing that mu A minus mu B is 0. So in that case we replace that with 0. Then the variances for A and B have been calculated as follows, such that the variance of A is 6.5. So you'll have 6.5 divided by, the observations are 10. So for each case, we took equal number of individuals to take the medicine, then plus 7 point, we can use 7.1, 2 decimal places in that case, divide by 10. So solving this expression gives us the T statistic as 0.8554. So then we need to go to the student's T distribution table, which is tabulated, which is available online with equivalent degrees of freedom. In this case, we have both N have 10 individuals. So we are going to have NA plus NA minus 1 being 20 minus 1, which is 19. So because this is what we call a two-tailed test, the two-tailed test is based on the null and alternative hypothesis. If you look at H1 there, what makes this a two-tailed test is this part. So if here I'm looking at not equal to, then this is a two-tailed test. If I had either greater than here or less than, then I would be talking of a one-tailed test. So if we are having a two-tailed test, like in this case, we have to divide alpha by 2. That is 5% over 2, which is 2.5%. So we will be looking at the tabulated value of the T at 19 degrees of freedom and 0.975 level of confidence, because again, a T distribution table being a form of a normal distribution, it is symmetric, and the value you read for alpha over 2 is the same as the one you read for 1 minus alpha over 2. So if I'm having 0.025, then it's the same as 0.975, hence this case. The value tabulated from the student's T distribution is 2.093, and therefore we go to the final step where we make a conclusion to either accept or reject the null hypothesis. So our conclusion, we said that under all circumstances we reject H naught if the T calculated absolute is greater than or equal to the T tabulated, or the statistic tabulated. This one needs not to be absolute. So in this case we've gotten 0.88, we've gotten 0.8554. The absolute value of this is less than 2.0, is less than 2.093, and therefore we do not have, the conclusion we make is we do not have enough evidence to reject H naught. So what is the implication? Change increasing the ingredient has no effect on the quality of medicine. So that's how you can make a conclusion where you have two groups you need to compare in a statistical inference case. Now, another method of statistical inference is ANOVA, the analysis of variance. Now, this technique helps in testing the significance of difference among more than two samples. The question is, here I had only two samples I had collected, but what if now I had 4 types of medicine, or the medicine in question had 4 types of ingredients I could alter or increase to check whether they help in improving the quality of medicine. That would mean that I take 4 groups of people, give them the old one group takes the old medicine, another group takes the one with 1 ingredient, the other group takes with the other ingredient, and so on, and then we check whether the 4 groups have a difference in the results we obtain from the people who have taken the medicine. Now, using ANOVA, it is possible to make inference about whether the samples are drawn from populations having the same mean. So what are the steps that are involved in ANOVA? One is to determine the H0 and H1. Of course, since the ANOVA tests is the difference between means, the hypothesis will be of the form H0, such that the first mean is equal to the second mean is equal to the third mean, and so on up to the last mean, or the last set of individuals that you're having. Then the alternative will be such that the means are not equal. That is, mu1, mu2, mu3 are not equal, where mu is the arithmetic mean of the nth population. If you have 4, then the 4th population. Step number 2, you calculate the variance between the samples. We label that as SSC. Then this is calculated as follows. First, you calculate the mean of each sample. If you have 4 samples, calculate the mean for the first sample, for the second sample, and so on. Then you calculate the grand mean. We label it X bar G. That is calculated as follows. Xg is equals to the summation of each of the means divided by the total number of observations in each group. So if each group has 5 observations, then you'll take the 5 means, sum them, then you sum the 5 observations, then that is 25, then you divide with the total. Now then, SSE is calculated as the difference between the means of the various sample and the grand average. So SSE is the mean of each sample minus the grand mean. Then square these deviations and multiply with the number of the observations in each group. So you square those differences between the mean of each sample and the grand mean, square them, then multiply by the sample for each group. We've said if they have 5, so you'll multiply the squares by 5 each. Then divide the total obtained in the step above with the degrees of freedom. In this case, if I have 5 samples, the degrees of freedom will be 5 minus 1, so that's 4. If you have k samples, then you do k minus 1. Step number 3, you calculate the variances within the samples. This will be denoted by SSE. Now, to calculate SSE, you calculate the mean of each sample, which we had found before. Then you find the deviations of the various terms in a sample from the mean values. Remember, in the previous step, we calculated the mean in each sample. Then we found the difference, then we calculate the grand the grand mean. Then we found the difference between the mean of each sample and the grand mean. In this case, calculate the mean of each sample, then get the difference between each observation, find the deviations of each various terms in the sample from the mean values. So you again take the observations now minus their means. Now square the deviations and obtain the total, which gives you the sum of squares. Now divide this by the degrees of freedom. For the errors, for the sum of squares due to errors, that is SSE, the degrees of freedom is the total number of observations. So note, if you have five sets or 5 samples and each sample has 5, then you will have a total of 25 observations. That's what we are labeling there with capital M. Then you subtract the number of samples. That is, in this case, if you have 25 overall observations and you have 5 samples, then it will be 25 minus 5, which is 20. And the definition, N is the total number of observations and K is the number of samples. Now, step 4, calculate the F. In such a case, when you have more than 2 means, we use what we call student's F distribution, which also an improvement of the standard of the normal distribution. So again, in this case, like in the T distribution, we use degrees of freedom, which you said is the number of observations minus the number of parameters you have estimated. So F is calculated by taking sum of squares due to errors divide by sum of squares due to samples, which we have shown how to calculate it above. Now in step number 5, you compare the calculated values of F with the tabulated values from the student F distribution with respective degrees of freedom and the level of significance. Of course, every test must have an associated level of significance. So we reject F, we reject H naught if the calculated value of F is greater than or equal to the tabulated value in the student's F distribution. Now, that information can be summarized in what we call an ANOVA table as follows. You have the source, this from the sample, which we labeled SSE. Then we have from error, we labeled SSC. Then from error, we labeled SSE. Then total, label it SST. Then degrees of freedom, we have said if it's from the samples, you take the number of samples, you minus 1. Then for error, you take the total number of observations, you subtract the number of samples. Then you get the mean square, where the mean square will be mean square for the samples, which is the sum of squares divided by the degrees of freedom, mean square due to error, which is the sum of squares due to error divided by the degrees of freedom, and mean square due to totals, which is SST over the total number of observations minus 1. Then you calculate the test statistic F as MSC all over MSE. We do an example on the same. Now, the following data relate to the yield of 4 varieties of maize, each sown on 3 plots. So you have 3 plots and you have 4 varieties of maize. Find whether there is a significant difference between the mean yield of these varieties at 5% level of significance. The plots are 3, plot number 1, plot number 2, plot number 3. In each of these plots, we are planting the 4 types of varieties, and then we are measuring the yield. Could be in kgs from each plot of land. Then we get the solution to this. Step number 1, every procedure for carrying out a statistical test of a hypothesis starts with defining H naught. We've said we are looking at equivalence of means. So since we have 4 types of varieties, then we'll talk of mean of A or mean 1, mean 2, mean 3, mean 4 being equal versus them not being equal. Now, we get the summation of the means. So note that we are looking at the varieties. So you sum this, it's what we are calling summation of X. You sum for B all the way to D. Then we get the mean of x, the mean of each of them. So by dividing 64 by 3, 65 by 3, that's how we are getting these values. Then we can get the grand mean. We've said you're getting the grand mean by summing the individual means, then dividing by the number of samples. We have 4 samples. So that would be 90.5 divided by 28.39. Then we can now calculate SSC. We said SSC is being calculated by taking the difference between the sample means, that is 21, 21.7, 23.2, and 25, and subtracting the grand mean, which is 28.39. Then each of those is squared and multiplied by the total number of samples we are having. We are having 3 samples and 4 varieties. So this is the first sample, the second sample, and so on. So we'll take the plots as the samples. Then, so SSC in this case will be, the first sample has a mean of 21. Then the grand mean is 20, sorry, this should be 22.7. So you do that, you get the grand mean minus each of the observations here, of each of these means here, 23. So that will give you a total of 28.29. Then we get SSE. So SSE is the mean of each of the varieties, you minus the observation of each observation in the sample. So the mean of the first variety is 21. So we will take 21, we subtract 20, we subtract 21, 19, and 24. They are here. You continue that way until the last one, which has a mean of 25. So you will do 30 minus 25 squared, 27 minus 25 squared, and the last one will be 18 minus 25 squared. Sum that, you get 219.84. Then we can now formulate it in tabular form, like the last during illustration. Now we have the sources, we have the sample, the error, and the total. Now for the sample, we've gotten 28. For the sample, we've gotten 28.29. That is the sum of squares. Then the sum of squares due to error, we've gotten 219.84. And then for the total, we have 320.13. The degrees of freedom, remember we had 4 types of maize, so that will make 3 minus 1, rather 4 minus 1, which is 3. Then the degrees of freedom for the error, we said, is the total number of observations minus the number of samples we had. The total number of observation, we had four varieties of maize, and we had 12 plots. So that makes 12. The total number of samples were 4 A, B, C, D. So when you go back, you go to this table, then we'll have for the degrees of freedom due to error is 12 minus 4, which is 8. And then for the degrees of freedom due to totals is the total number of observation, 12 minus 1, which is 11. Then we need to get the mean squares due to each of the sources. Mean squares due to sample is you get the sum of squares, you divide by the degrees of freedom. So 28.29 divided by 3, you get 9.43. Then we have mean square due to error. That would be the sum of squares due to error divided by degrees of freedom, which is 8. So then we calculate the F value, the test statistic F, by getting the mean square due to error divided by the mean square due to the sample, which is 3.85. Then we need to get the corresponding value from the student's T distribution. No, sorry, the student's F distribution. And the student F distribution has 2 types of degrees of freedom. So the first one is from the sample, and the other one is from the total number of observations. So if you go to the students F at an alpha of 5% divided by 2, of course, due to symmetry, then, and you consider these 2 degrees of freedom, the students F distribution table is available online, then you'll get a corresponding value of 8.84. And therefore, since this value is less than the tabulated value, like in the other cases, we do not have enough evidence to reject H0, and therefore the means from the plots are equal, and therefore the 4 varieties of maize tend to have the same yield in the 3 plots. Then we look at another distribution called the chi-square distribution. This distribution is used as a test statistic for hypothesis consisting of the difference of a sample, a corresponding, it's used as a test statistic for hypothesis consisting the difference of a sample to a corresponding set of expected or theoretical frequencies. So in this case, you'll have the actual observations and you will have an expected observation from the sample. Then you'll check how different the observations are from what you expected. Now, the distribution is used, the distribution, that is the chi distribution, is denoted by sigma, by the chi symbol, the Greek alphabet chi and a square. So, and it has the following properties. Number 1, the distribution is similar to the T distribution, where the critical values vary with the degrees of freedom. So the degrees of freedom are the values that change. Like the way we said in the normal distribution, what changes is the mean and the variance. In this case, it's the degrees of freedom. Now, 2, the distribution has an additional property that the sum of 2 chi distribution, if you have a set of random variables following a chi, and another set 2 following a chi, then you can have the 2 having a chi distribution with the degrees of freedom being the sum of the degrees of freedom in both the distribution, which is important when you have to compare two tests which have the same chi distribution. You can use them as one with the degrees of freedom being the summation of the 2 individual distribution. If the degrees of freedom are less than 30, the distribution of the chi is positively skewed to the right. And for degrees of freedom greater than 30, then the values of the chi tend to behave as a normal distribution. So for degrees of freedom greater than 30, using a chi is equivalent to using a normal distribution. Then how do you carry out a chi test? Now, the test for the chi is defined as the summation of the observations minus the expected squared divided by the expected value. So this value is compared to the tabulated value. This table for the chi is available online. So you compare that to the value tabulated in the chi distribution table and make conclusion as before, that if the test statistic for the chi is greater than or equal to the tabulated value, then we reject H0. So we can look at an example on the same. Now, the number of workers required in a manufacturing factory was found to vary from day to day in a sample study. The following information was found. So this is a table representing the number of workers who are required in a manufacturing plant. Now, day 1, Monday, Tuesday, and so on. So we have Monday, they required 1124, Tuesday, they required 1125, and Saturday, the number reduced to 1,118. The total for that, which I included in the table, is 6732. So now we need to evaluate the test statistic so that we can use it in making conclusion. Now, consider the hypothesis that the number of workers does not depend on the day of the week. So if we end up accepting H0, then we will conclude that the number of workers is independent of the day of the week. You don't need to know whether it's a Monday, a Tuesday, a Wednesday, or so on to know the number of workers you need. Now, the expected number of workers per day is sum the number of workers in every day, divide by the number of days included, which is 6, which becomes 1122. Then we evaluate the chi-square test statistic, that is the observed values as in the table. Then the expected value is repeated all through because it's the mean. Then the difference squared, so 1124 minus 1122 is 2. You square that, you get 4. So, and so on, up to the last one, which is 4 squared, 16. Then you divide that again by E. So whatever value 4, you divide by 1122 to get this value. Then we sum these values. We sum these values to get the test statistic. Now, the tabulated value from the chi distribution with the degrees of freedom 5 is 11.07, and therefore we accept H naught that the number of workers is dependent on the day of the week. Thank you.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.